All right, good morning. My name is Mary Thomas. I'm a recently retired principal. I was principal at Jersey High School for the last 10 years principal, 2 years assistant principal. Before that, I was a math teacher in the district, and I also have a decent science background. I almost was a math physics major and decided not to go that way, to stay with the math. Basically, today we're just going to kind of review, pull the things together to help you with the test for tomorrow. And you guys are high school, middle school. You've done, and you're probably more of an expert than I am. I've had extensive college chemistry, but that was 40 plus years ago. My role in the grant, I'm new. In fact, I did not make it to Goddard because I'm that new. It was between the two. I will be the coach for the Central Region. So any of you here from Central Region? Okay, then I'll be seeing you again on the 12th. First thing today, we're going to look at a video that was put together and funded by the Annenberg Foundation on the periodic table. It is definitely dated. It was probably about 1990. The information in the video is pertinent. Some of the video was very easy to give elementary people some ideas of how they could do a lesson. I don't think I have that need at this level because you guys are probably you're more of an expert probably than I am.
How do we make sense of this extraordinary...
Oh wait, that's not where I want that to be. That's wrong. I want the one that starts at the beginning.
Annenberg Media.
Additional funding provided by the people of Dow, the company that lets you do great things. The 8,000 scientists of the Eastman Kodak Company. The Exxon Education Foundation on behalf of Exxon scientists. And...
Okay, where'd the sound go?
I'd like to show you the most important piece of equipment that you're likely to encounter in a chemical laboratory. How much do you think it'll cost? Was it invented in the United States and made in Japan? Are you ready? Let's see. Here it is. This is it. Not a superconducting super collider, is it? Not a piece of equipment that's worth $100 million. Just a piece of paper, a chart, an idea, a tool for the mind. This was invented by Mendeleev, a Russian, 120 years ago. It's called the periodic table, and it's worth more to chemists than all of the pieces of equipment in our laboratories. What are the properties of the substances in the world around us? There are two types of properties. Chemical properties refer to the element's ability to combine with other elements and form compounds. Physical properties include density, hardness, melting point, boiling point, and conductivity. Each element is different from every other element in its chemical and physical properties. This uniqueness can be traced to the atomic structure of the element. But some groups of elements also share common properties that vary systematically and predictably. These common properties are the basis of the modern periodic table. There are 109 elements in it. 88 occur naturally. The other
We're 118 or 120?
For centuries, Latin was the common language of science, so many elements have Latin names. For instance, iron was ferrum, so its abbreviation became Fe. Gold was aurum, Latin for shining dog, so it became Au. Madame Curie
Dawn.
discovered an element and named it after her native Poland, polonium. And more recently discovered elements have been named after famous people, such as Einsteinium, named for Albert Einstein, and Nobelium, named for the man who established the Nobel Prize, Alfred Nobel. Besides a symbol for the element's name, in this case helium, each box also contains some important numbers. Notice the number below the He symbol. This is the atomic mass of the element, the total mass of the protons and neutrons. All helium nuclei contain 2 protons. However, the number of neutrons may vary. For example, there's a rare form of helium which has only 1 neutron in the nucleus. The 2 varieties of the same element are called isotopes. The atomic mass of an element is the weighted average of the masses of the isotopes in the naturally occurring element. The number over the symbol in each box is the atomic number of the element, the number of protons in each nucleus.
An atomic number is what determines an element's position in the table. The elements in the table are arranged in order of ascending atomic number as you go from left to right. Here we have hydrogen, number 1, way over here helium, number 2, then lithium 3, beryllium 4, boron 5, and so on across the neon tint, back to sodium 11 and magnesium 12 and so on, left to right. Now there's another facet to the table. Because of the way it's laid out, each element is a member of a group that goes up and down the table and a period that goes across the table. For example, potassium is a member of this group and is a member of this period.
There are 7 horizontal periods running from left to right. Each one has been assigned a number, which is placed at the left of the period. 14 of the elements in periods 6 and 7 are pulled out of their place and laid out below. If they were placed in the table, it would look like this. So it makes it much easier to arrange the table if they are at the bottom.
There are also 18 vertical columns called groups or families. Each group is designated by a number and a letter, which is placed at the top of the column.
Elements within a family all have similar properties. To demonstrate this, let's look at one family on the far right of the periodic table, the noble gases.
These balloons contain the first 5 noble gases. We have helium, neon, argon, krypton, and xenon. Now we're missing radon because it's radioactive. We're all familiar with helium. It's used in balloons and blimps. The rest are used to fill various light bulbs and lamps. But what are some of the properties that they have in common? Well, they're odorless, and they're colorless, and they're all quite unreactive. And as you go down in the family, each one gets heavier than the previous one. Let me show you what I mean. This is helium. Here it goes. This is neon. It's somewhat lighter than air. There it goes. Now, argon and krypton are both heavier than air. And xenon is the heaviest of the ones we've seen. It's the proverbial lead balloon.
You can begin to see the different types of information that can be derived from the periodic table. But how do chemists use the table in their work? Glass making is one example. At one time in the ancient world, glass was so rare that it was prized more highly than jewels or gold. But as we mastered the techniques of glass working, glass became a commonplace necessity. The types of glass multiplied tremendously, so that today, glass comes in many forms and colors. Artists use it to create new and intriguing constructions. Craftsmen mold it by hand into the elegant forms of Steuben crystal. And factories manufacture glass for countless everyday uses. Basically, different types of glass are made by mixing silicon dioxide, sand with different metal oxides, then melting them together. The choice of the oxides, which determines the characteristics of the glass, is guided by the periodic table. Dr. Jerry Fine is a glass chemist at the Corning Glass Works in Corning, New York.
I cannot imagine working without the periodic table because scientists are interested in looking for systematic relationships between different substances and between different elements. The periodic table is a simple way of looking up and finding systematic relationships between different elements that we can understand on a very simple level.
In the Glass Research Center at Corning, thousands of samples are poured each year as new types of glass are developed and perfected. One group of elements frequently used to make glass is on the far left of the periodic table, the alkali metals. By mixing in different alkali metals, glass with different characteristics can be produced. So understanding their variations in behavior is important to glass makers, and indeed to all chemists.
We call this family the alkali metals. They make up group 1 in the periodic table. The first element is lithium, and then there's sodium and potassium. Down here is rubidium, and this one is cesium. Now, do you notice anything that they all have in common? You probably see that they're all stored in very unusual ways. And the reason we do this is because they're all highly reactive. I have here 3 containers of just water. And I'm going to take a piece of this lithium and put it into the water. Watch what happens. Oh, it starts to fizz a little bit. The fizzing now is the reaction of lithium with the water to produce hydrogen gas. Let's try the sodium. I'll get a small piece of that. Not too big because we don't want the reaction to be too violent. Oh, that reacts much faster, doesn't it? See the sodium bouncing around there, again fizzing, giving off that hydrogen gas. Okay, let's try potassium, the most reactive of the 3. I'll get a small piece of that and put it into the water. Wow! That really reacted. You see the immediate reaction of the potassium. Again, it's formed that hydrogen gas, and the hydrogen gas will ignite.
So the alkali metals all have similar chemical properties, but they also vary systematically. As you go from the top to the bottom of the column, the atoms of each element become larger. Chemists can use this characteristic to increase the strength of their glass. The size of an atom increases as we go down any column. In the alkali metal group, the atomic size increases from lithium to sodium to potassium and so on. But as we move across a period, starting with an alkali metal, the size of the atom gets smaller and smaller until we get to a new period. Here we see a jump in atomic size in the next alkali metal, and again a decrease along the period. This pattern repeats itself throughout the table and is called periodicity.
Everyone is aware that glass tends to be a brittle material. If you've ever thrown a baseball through a window, you know that the glass breaks quite readily. However, there are ways of taking that simple window glass, which is made of sodium, calcium, and silicon, and treating the glass to make it strong. One way we do that is by use of the periodic table. If we take that glass that contains sodium and substitute potassium in the surface for the sodium, or substitute an element that behaves basically in the same way, but is slightly larger, we can enhance the strength of that glass and make strong glass.
The results of this process are quite easy to demonstrate. If a steel ball bearing is dropped from 1 foot onto glass made with the alkali metal sodium, watch what happens. The sodium-based glass shatters completely. Now watch what happens if the same ball bearing is dropped on a piece of glass where potassium has been substituted for sodium. This time, the ball will be dropped from 20 feet.
The way we do that is by taking the glass which contains sodium and dipping it in a bath containing molten potassium. What happens is the molten potassium substitutes for the sodium in the glass on the surface of the glass. Because from the periodic table we can tell that potassium is larger than sodium, the potassium atom literally stuffs the surface of that glass.
The predictive ability of the periodic table was first demonstrated by a Russian chemist, Dmitry Mendeleev. 100 years ago, he developed the predecessor of our modern table. Mendeleev's table included all the elements then known and was consistent with their varying properties. For 3 undiscovered elements, he left blank spaces, predicting that they did exist and that their properties would be consistent with their position in the table. For his time, it was an amazing hypothesis. One position that he left blank was this one for gallium. Based on the properties of the 2 neighboring elements, aluminum and indium, Mendeleev was able to predict some of the properties of gallium. He was also able to predict 2 other elements, germanium and scandium. When the elements were discovered and their properties measured, Mendeleev's predictions were found to be remarkably accurate. In this century, another chemist, an American, rearranged the structure of the table based on the properties of elements that he himself had discovered. His name is Glenn Seaborg. In 1944, the periodic table didn't look like it does today. The periods and groups were laid out differently.
Back in the days of Mendeleev, and actually extending into the 1930s, the heaviest elements, thorium, protactinium, and uranium, were put into the periodic table up in the body of the periodic table under hafnium and tantalum and tungsten. And it was my idea in 1944, while I was working on at the Metallurgical Laboratory in Chicago on the Manhattan Atomic Bomb Project, that these might be misplaced and that they might be the first 3 members of the actinide series. And then I boldly, and against the advice of some of my eminent inorganic chemist friends, plucked those out of the body of the periodic table and put them in the row below, and then continued that with 93, 94, and so forth, up to 103.
The idea to rearrange the table occurred to Seaborg late one Friday afternoon. He was drafting a classified report for a seminar the following Monday, and he decided to include this idea in his report.
I presented this at that Monday seminar, and it went over like a lead balloon. The idea that one would be brash enough to change the periodic table after all these years in this fashion, when everybody felt that thorium, protactinium, and uranium should be in those sacrosanct positions up in the body of the periodic table under hafnium, tantalum, and tungsten.
His discoveries of the new elements remained classified until after World War II. When he was able to publish, he incorporated his new arrangement of the periodic table.
I showed this periodic table to some of my friends, the most eminent inorganic chemists in the world, and told them that I planned to publish it, and they said, "Don't do it, Glenn. It's wrong. It will ruin your scientific reputation." Well, I'm fond of saying that I had an advantage. I didn't have any scientific reputation at that time, so I went ahead and published it.
Seaborg's new arrangement enabled him to predict the properties of still more elements. His ideas were later verified when the elements were produced artificially. Seaborg was awarded the Nobel Prize in Chemistry in 1951. His rearrangement is our modern periodic table, and what ultimately determines the position of an element in this modern table is the way the electrons are arranged in the energy levels of the atom. As we move through the table and the number of electrons in an atom increases, the energy level diagrams contain more and more levels and sublevels. Both the number and types of electron clouds increase in complexity. For example, this is the energy level diagram for hydrogen's 1 electron in an S cloud called the 1s. Lithium's 3 electrons are diagrammed like this. 2 electrons in the 1s cloud. Each cloud can contain 2 electrons. Then the 3rd electron is in another cloud, an s cloud at the 2nd level. Let's move forward to sodium and look at an energy diagram for its 11 electrons. Its first 2 electrons are in the cloud at the 1s level. Its next 2 electrons are in an s cloud at the 2nd level. This is actually only the first of 2 sublevels at the 2nd level, so it's called the 2s sublevel. The next 6 electrons of sodium are in the other sublevel, called the 2p sublevel. Notice the number of clouds in the 2p sublevel. There are 3 p-shaped clouds in it. Each of these clouds contains 2 electrons. Where does sodium's 11th electron go? As we move higher on this energy diagram, we encounter the first sublevel of level 3, the 3s. It has only 1 s orbital in it. Sodium's 11th electron goes here. When chemists diagram energy levels of electrons within an atom, they replace the figures of the clouds or orbitals with blank lines. Arrows are used to indicate the presence of electrons in each orbital. This is the diagram for sodium's 11 electrons. Sodium is the 2nd alkali metal. Note that it has 1 electron in it, and any atom are called its valence electrons. The noble gases are another example of a similarity in outer electron structure. They have a filled s or p sublevel, a very stable arrangement. Next to them is an important group called the halogens. They are all missing an electron from an almost filled sublevel, which makes them very reactive. Now, as the number of electrons in an atom increases, what are the rules these electrons follow in filling different sublevels and orbitals? To find out, Don Showalter went to St. Albans School on the grounds of the National Cathedral in Washington, D.C.
We're out here today to show you how the electrons fill up the various energy levels that you just saw in that diagram. And to help us out, we have these 11 baseball players. Right, Coach! All right. These baseball players are now going to represent electrons. And we're going to have an electron practice. They're going to practice the rules that chemists use to fill the various energy levels. Now here's the ground rule. These bleachers represent the various energy levels. The lowest one being the 1s, colored blue. 1s! Right. The next energy level is the 2s. It's colored green. 2s! All right. Now the 2p has 3 sublevels, and it's colored red. 2p with 3 sublevels. Good. And we've got the highest energy level is the 3s, and it's colored yellow. 3s! All right. Now there are 3 basic rules that we have to follow. Rule number 1. Electrons fill lowest energy level first.
Electrons fill the lowest energy level first.
Okay, here's rule number 2. No more than 2 electrons in any one orbital.
No more than 2 electrons in one orbital.
Beautiful. Here's rule number 3. If you have more than 1 orbital in a sublevel.
If we have more than 1 orbital in a sublevel.
1 electron in each orbital before you double up.
1 electron in each orbital before you double up.
Great. Have you got it?
Yeah, Coach.
All right, let's get energized. The first element is hydrogen. Go.
Hydrogen has 1 electron, so it goes in the lowest energy level available, the 1s.
Now we're going to skip to nitrogen. Go.
Nitrogen has 7 electrons. The first 4 fill up the 1s and the 2s. But what about the next 3? 1 goes in each of the 3 2p orbitals.
Now we'll skip ahead to sodium. Are you ready, team?
Yeah, Coach.
Go.
Sodium has 11 electrons. The first 4 go into the 1s and the 2s. The next 3 go into each of the 2p orbitals. Then numbers 8, 9, and 10 go in. Finally, the 11th electron goes into the 3s sublevel.
And that's the way the electrons fill the energy level. Right, team?
Right, Coach.
Scientists at the Smithsonian Museum have applied a technique that uses information about the energy levels of different atoms to study works of art. This technique analyzes the elements in different pigments and is called X-ray fluorescence. Jacqueline Owen is a chemist at the Smithsonian.
If, for example, you were to know an artist's work so very, very well that you knew that that particular artist never used a particular pigment in all the paintings that have been studied, and there's a painting in question, one might analyze a painting to determine whether or not that pigment, a pigment that's not characteristic of that artist, is present.
X-ray fluorescence involves bombarding the atoms in the painting with X-rays, causing them to eject an electron. To see exactly how this happens, let's return to the electron team. Here are the electrons in their energy levels for the element sodium. As an X-ray enters the atom, it knocks out an electron in the lowest orbital, the 1s. When this happens, some of the electrons in higher energy levels fall to lower energy levels, filling the gaps. As the electrons cascade down to lower energy levels, they give off an X-ray pattern that is characteristic of each element. Instruments analyze these X-rays and identify what element is present.
It's very nice to be able to quickly and easily find out what some of the elements are that are in the painting, because we have looked at the painting in terms of the colors we see, and we'd be interested to know if that blue is a copper-containing blue or a cobalt-containing blue, and that can be done readily by using X-ray fluorescence to identify the elements present in that area. So it's a nice technique for non-destructively and quickly identifying some of the elements present in the painting.
To review, the elements in the periodic table are arranged in serial order according to their atomic number. The rows are called periods and the columns are called groups. The size of the atoms increases as we go down in a group and decreases as we go across any period. This is an example of a periodic property. Elements in any group have similar arrangements of electrons in their energy levels. Therefore, they have similar chemical properties.
You can see right away that a given electronic configuration implies similar properties. For instance, the alkali metals, with their one electron in the s subshell, they all readily give up that electron, and no more than one electron. And all of the halogens on the other side of the periodic table, with their missing electron in a p subshell, readily accept such an electron. One might ask, why do we concentrate on the outermost electrons and not all the other ones? It's because the outermost electrons are at highest energy. They're furthest away from the nucleus. In them is chemistry.
All right, now even in that little video there, the E-team is certainly something that elementary, middle school could do, maybe even high school if you get a little, it depends on how crazy your kids are at the high school. But you wouldn't have to be outside. What would all you would need? Oh, there's a pair of steps. It's a pair of steps. And so in middle school, you could create some type of a lesson talking about atoms and your energy and show them this. You don't have to get into super detail. High school you do, but at the middle school level you wouldn't. So there's one thing that you could very easily incorporate, and it probably wouldn't take a long time. It could be an enrichment thing if there's not anything in your curriculum at this point. End of a day, try something. Oh, I need 15 minutes to fill or a half hour to fill. But there is a suggestion for you. All right. Now remember, the test tomorrow is the same test that you took at Goddard or wherever it was that you took it. They do have the periodic table with them. It's this, you will be getting this table with the test. And then you again take that test in May. So what we're looking for is we're looking for growth. And so you may or may not have done this correctly when you did it before, but hopefully you'll do this section pretty easily tomorrow. All right, we're going to review a little bit here, the orbital. One thing I want to say about the video with the E-team, depending on the age level of kids that you're working with, he didn't identify, you could do that, but he didn't identify Pauli's principle and Hund's rule. He just told them what the rules were, so he didn't actually give them formal names. And depending on the age level, that might be something you may or may not want to do. All right, our orbital diagrams is one of the things that you will do. You'll do a couple things on tests. I think you create them, and I think you identify whether they're correct. And do not go very high on the tests. The second sheet that she gave you helps you fill them in. Remember, if you're getting into some of the elements down here, you're just following the structure. The 1s's fill in, 2s, the 2p suborbitals, 3s, 3p, and so on. And when you're down, like when you look at period 4, the 4s's start the period, then you fill in with the 3ds before you fill in the 4p's because the energy level is higher on the 4p. So this is just some examples here and how you're filling these in, which you people should be very well with that. Remember, one spin goes up and one spin goes down. When you're dealing with suborbitals that have more than one orbital, the spin starts by being the same. Doesn't matter whether it's up or down. The convention that we usually use is to start with the up first. All right, here are some examples. This one is a correct one. There's only one in the 2s and they started it up. Would it matter if they started it down? No, it would still be correct. Here's where they show you one like that. Letter B, the 2p, they filled it up by starting down, and that's fine. It's not the normal convention. C is incorrect because the spins are wrong. The spins have to be going the same direction. And it wouldn't matter which one that you would change to make it correct. And D is also correct. And the sublevels, as before, you have to fill in each orbital before you can fill in, go back and fill in. This would be incorrect, as this one would be correct. And that's your Hund's rule. Here's another one. Orbital to 2p, there's 3 electrons, so there's 1 in each orbital. This is incorrect because it has filled the first orbital before it filled 1 in each. All right, and this last one is incorrect again because they did not fill 1 in each of the orbitals in the 2p sublevel. Here's a picture of nitrogen in color showing you and this is done correctly. Again, in the 2p sublevel, you could have them all going down. Are you looking at this grouping? Orbital design is, but I'm not sure. I haven't seen the test, so I'm not sure how the questions are on. I'm not sure how the questions are on there. Another thing, and elementary probably uses this all the time. I don't know about the high school as often, but one of the things in your RTOP model is for engagement in the class. So if you have something like this, something very quickly you can do is a thumbs up or thumbs down. So all of people are participating. Is this correct? Thumbs up or thumbs down? And you can see who's paying attention and who's not paying attention and who's not participating. So this is incorrect because of the 2p. And you can do one of two things. You can either change this one to make that up, or you could change the other two to make that down. So, correct or incorrect, up or down? What's incorrect? It has to fill in the first two. It has to fill in these before it can pair them up. Correct or incorrect? I'm not going to do thumbs up, thumbs down, but that's just something for you when you're in your art, when you're being observed, that you would have. It could very quickly get everybody engaged. What's wrong with this? The spin. The spin is wrong. You're either going to change this one or you're going to change these two. Correct or incorrect? Incorrect. Whoops. Again, you need to correct. One has to go up, one has to go down. Correct or incorrect? This one is correct. It's oxygen, isn't it? What's A? Oxygen. All right, now either in pairs or your table or by yourself, let's draw the orbital designs for the following elements. I'm going to caution you on bromine, and this one may be a little harder for you, but some of you probably not. So I'll give you about 5 minutes and we'll go over those. Remember to use, if you use this chart, it'll tell you what your last suborbital is. For example, calcium. Calcium is going to go to the 4S. You're doing the orbital design with the arrows.
What is that called? What is the verbiage for a question that would ask for that? Electron configuration.
Are we all down to at least the last one? Are we all down to at least bromium?
No, calcium.
Okay.
Like bromine's over here, we didn't do any 4D configuration. I mean, 3D, we didn't do any D configuration.
A hint on bromium is check out this table here that she gave you. Where are we going after 3P in the bromium? 4S. Then what comes next? How many is in the D? How many or? All right, let's just quickly go over these. Now we're going to assume, middle school and high school, you know that everything is filled in but the last orbital. So let's look at lithium. How many electrons are in the 2s shell? One. Does it matter up or down? All right, fluorine, how many are in this last shell? So it's 1, 2, 3, 4, 5. Oxygen, how many in the 2p subshell? 4. Can I just erase this? No. You have to fill them up, fill all 3 first and then go back. Calcium, how many in the 4s? It's full. Now again, we assume you already filled in all of these. And some of the ones like we did, if you're looking to see are these correct, you're looking to see that the spin is correct, that everything is filled in. If they've only filled in one here and then fill this in, that would be an incorrect. That's the types of things that you'll be doing on the test. All right, let's look at this one. What's the atomic number? So we're going to get all these filled in. And even though you know that these are going to get paired, don't get in the habit of trying to pair them. Follow the rules so that you don't make a dumb mistake. All right, what do we have here? How many electrons so far? 18. So we have 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. All right, let's take this and do the electron configuration. What am I going to start with? we're just going to take all of these and put the number of electrons with the letter. So we have 1s2, 2s how many? 2p, 3s, 3p6, 4s, all right, what's the next thing I'm going to ask you? Give me the shorthand or the shortcut. Where am I starting? Would be nice. Prepton's right beside it, but we have to go back to argon. And argon is what atomic number?
18.
All right, so that takes us out. That takes us out to here. So we have the rest of the. I don't know how many are middle school in here. Right now, I don't know what grade levels, how low your middle school goes, but one of the things that, another suggestion that you could do with something like this, if you want to incorporate, you can incorporate it as a math lesson and pull in the elements and the periodic table beside, is you could do something like what's the element or find the element. And you could have these, you could have a series, and I would use ones that the kids would know. Oxygen, iron, some of that thing. You could have a series of orbital designs, and then underneath it, you could make this a math problem. You could just make them count the electrons, and then when they get out here and they get the atomic number, what's the element? So there's something else that you could do that would not be long to do, but, and I'm sure you people have many more ideas than I do, but it's just something to give you a little start. And that's basically what this next one is looking at the electronic configuration. Here's the periodic table, the one that this is the second one that she gave you without the elements, looking at the orbital. Here's another way of looking at the orbital occupation of the orbitals. And this is basically a shortcut, and the problem with shortcuts is if you don't remember how to set it up correctly, then you're doing it wrong. But this is another way, and where they set up each of they took the S's and the P's and they wrote them in order of where they would start on their period. And then they drew the arrows, and I'm doing this on here, and they drew the arrows as to how the fill happens. So 1s fills up, then the 2s fills up, then 2p, 3s, 3p, 4s, then we go to 3d, and that's what happened on bromine. 4p, 5s, then the 4d, 5p, 6s. So this is another, on the test, I don't think you go past the 3s. I'm not even sure you get that high. I think you might stay in the 3s or 3p, but here's another way of looking at how those electrons fill in. Pauli's principle, you're okay with that. You're filling them in the suborbital, you're filling in one at a time. And if you do that situation with the kids, like they did on the video, make sure, and when they get into that suborbital that has 3, first, they go into each orbital first, and then the second one fills in. Your first is the S's, and they go from 1 to 7. Then the next one is the P, and they go from 2 to 7, lining up with the numbers. The D's go from 3 to 6, and the F's go from 4 to 5. I know she has the first PowerPoint up on the wiki. She will put this one up, but I don't know that she put it up yet. I didn't get a chance to look today. She was kind of waiting until most of you got through it before she put it up. Well, some of you are still doing this. If I give you something like this and I ask you what's the element, what do? Add up the electrons. That gives us what? The atomic number. From the atomic number, then you can look at it on the chart. Now again, on the test, if they have something like this and say, is this a correct electron configuration? And I put something like this, you know that that's wrong because this has to be filled before this can be filled. You know the S's have 2, the P's have 6, the D's have 10, but I don't think you're going that far. The F's have 14. So that's the thing that you would want to look for in something like this. Or it might come back here and say an S of 1. That has to be an incorrect electron configuration. So those would be the types of thing that it would do. All right, this is all review. And you do those very well, I think. Here are the exceptions, and those were the asterisks. You don't need to know these unless you're the chemist, and then you would know them. You would have, you'd have information to get those. Here are some other ones. Here's iridium, and that goes all the way down to 5D. Look, you have the 3D, the 4P, then 5S, 4D, 5P, 6S, 4F, and the 5D. We talked about the electron notation, and I don't see you guys having any problem with that. And even the shortcuts. All right, I want to do number 2. Do the electron configuration of iodine. Electron configuration of iodine. Take a minute, do it with a partner, do it by yourself. And you can do the shortcut. You're going to start with krypton. When are you starting with after the krypton? What orbital? The krypton's in period 4, so then you're going to period 5, so you're going to start with what? 5? 5S. Some of the things, sometimes when I'm doing these, I put my number right here so I can start counting across and know where I'm at. I mean, that's not part of it, but you know that you need to have, for iodine, we need 53 electrons. Question? How many S's for 5? How many D's? 10. How many P's? And then you can check yourself to see if that's 53, which it is. Now let's answer the second part of the question. How many electrons, unpaired electrons, does iodine have? What is the only piece of information that you need to know for that? The most outer suborbital, and so this is all that we need to look at. How many should, and if you need to draw that one, you can. Most of you should be able to do that without drawing it. So how many unpaired electrons? 1. All right, now for about the next 10 minutes, do a couple things. She wants you to go out and look at this periodictable.com, and if you have your iPad, you can go out and do that on the internet. You can get this from iTunes for $13.99, but most of you in your classrooms have internet available to you. And pick an element that you don't know anything about or haven't heard about, and just check it out. Check at least 2 of them. And the other thing would be to download, if you haven't, Nova Elements. I would say middle school would use this more than high school. And play with that a little bit. This is free, Nova Elements. And you can do this with a partner, share the information.
Finish up that when you were talking, and it didn't register to me what you said to do now. What did you say we're supposed to do now?
You can go to this periodictable.com. I'll bring the PowerPoint back up.
Okay.
Go to the periodictable.com, which is that picture, and just pick a couple elements that you don't know anything about. Yeah.
Okay.
Or the Nova Elements, either one or both.
Okay.
The name is not hard because of totally get but as soon as they mix, they pick one that they like and they need every that's all my bottles have. It's not hard. Well, yeah, I look back.
There's questions on there, but we thought you covered them. So why are we doing two posts?
Randy on that.
Any of you used the Nova elements before? I think there's a lot, especially in defining the elements, there'd be a lot of little nice clips to, and then they have you build elements. Depends on what the grade level is. Have you used the periodictable.com? Some of you chemistry people probably have. One last thing I want you to take and talk about among your group is what are some lessons you could do from this within your classroom for your age level? What are some ideas? And we'll just ask you to share one. So I'll give you a few minutes to discuss that and then we'll share.
Can you clarify that ideas
On how you would incorporate, what kind of lessons you could do with any of the information, or either the orbital design or the electronic configurations or dealing with the elements. Because that's one of the things you're going to have to do. You don't have to take this class, though. I mean, you can use it from any class. And not elaborate, just something like you could, we did from the example, the E-team. We could show electron energy and the orbital design by having a pair of steps and using students from that aspect.
It's just better.